So yeah, we have some great speakers tonight, and we're going to start with Brendan McCord. He works for Evolv Technology, and they're doing some really great work with security. So I'll let you take it away. Thanks.
Thanks. So it is. It's an honor to be here at the inaugural event. I'm looking forward to hearing Rob talk and to sitting in on a lot of these more in the future. I'll keep it pretty informal, both because I think that's how it works best, and also this is a really unique space, and we'll line up every year. So this is the last time you guys will see my face. But no, it's exciting. So we are. So I live downtown, but commuted back in from Waltham. We're based 15-20 minutes or 2 hours depending on traffic from where we are here, and we're working on kind of a unique machine learning application, which is in physical security. So we're trying very, very hard to change the status quo there, and I'll tell you a little bit about what that really involves from a vision standpoint. Everybody's familiar with the touch points of security and how frustrating they are today. But I'll tell you how we think about it as practitioners, and then get into what are the interesting machine learning problems that we're tackling along the way. So first, the user problem that we're solving, or the market problem that we're solving. Threats, when you think about threats, if you're a security director, you are now, in 2016, 2017 timeframe, dealing with something that is really, really inexpensive, asymmetric, very easy to kind of cause damage. If you think about the technology that's required to do harm versus the technology that's required to actually show protection against it. And it's hugely distributed in nature. But the security apparatus that we built for ourselves after 9/11 is anything but. It's very, very centralized. A couple of places like an airport checkpoint got the lion's share of the security focus, and there's just this big mismatch. And for people in security, they're having to work harder than most people in keeping up with the pace of innovation. So, the question you have to ask yourself is this new normal kind of okay? And the new normal is long lines, not just at the airport, but everywhere. It's false alarms, because the technology in use doesn't pay off on the promise of its vision. It's missed threats, because the threats are constantly changing, and it's incomplete coverage because it's still largely human. A lot of it is people sitting at a facility trying to provide coverage, and they just can't. So it's not about more people, more time, more money at the problem. It's about a smart, practical application of game-changing technology. Kind of this I think makes sense to most people, that there's a threat. It was an airplane. We put a lot of stuff in to try to find switchblades and tiny little bits of explosives to do that. The current threat today is not that. It's something that is much more distributed, and it's about people who can cause mass harm to folks in crowds. So before I talk about who are we, so when I was sitting there reading, kind of just rereading this, I was hearing conversations about machine ethics, about anomaly detection, about chatbots and things like that. And I think that's one of the strengths of this group, is that it's not a niche group. But I wanted to ask how many people would say that their primary focus is in the realm of visual recognition. So nobody. Okay. All right. So try not to let that make me loosen this one. And, no, but so
I was in a room absolutely chock full of visualization people yesterday.
Okay.
The last meetup.
There you go. So that some of that rubbed off. But so okay, well that's helpful. So I'll go through kind of from first principles, but quickly. So about me, I had a sort of technology background in nuclear, some frontline stuff in the military. I head product at our company, which means I'm very, very involved with the AI. I manage the team of developers that does that. We've got some really smart PhDs in a variety of disciplines and non-PhDs working on this. So just really quickly, why I think this is neat. Again, I heard somebody talking about like Navy SEALs with cyber people mixing together. Our team is the guy on the left. Founded the company that does your explosive detection for bags when you go to airport. Like if you go to Logan and you check a bag, it does explosive detection. Built that company to 100 million in revenue, sold it. The guy on the right was a technical lead for the Game of Thrones and Star Trek mobile games. So a really neat mix of old and new thinking, kind of brought together for a pretty unsexy but important problem. And our supporters are some of the biggest names from CIA, NYPD, Secret Service, et cetera, and they work really close with us. So shifting to what are we building before going into kind of the technical problems. Security isn't complicated. You just have to do a few things really well, and it's very, very hard to do those things. So it kind of comes down to spotting the bad guys, keeping people out of places where they shouldn't be, finding guns and bombs, and getting intelligence or information that is actionable to people who are on the front lines. But you have to do it in a way that minimizes inconvenience to the public, and you have to do it in real time. So we think about this pretty expansively as a broad platform that includes these core elements: sensors to get information on the reality of the situation, AI, human judgment, and I'll talk a little bit about that, but that's a key part of our systems thinking approach, and then get it to the front lines. We work in buildings like this, like stadiums, train stations, and we think about it in terms of layers. And then we use different sensors. So what follows is, we build some of our own hardware, and that puts us in a unique position for machine learning. We use existing hardware like cameras, because there are a lot of those, like 300 million that are already out there for some security purpose that are sort of not doing much. And then we can deal with other incoming data streams. But the top two there are the kind of the primary sensors that we use today. So, what are we building? Well, we built the world's first active millimeter wave video frame rate, meaning you can just walk through this thing as normal walking pace. You don't have to take your wallet, phone, keys out of your pocket, and it'll detect threats, guns, explosives, suicide vests, firearms. I think they say guns and firearms. And then it scans at the pace of light. It's really fast. It's built for kind of like Amtrak type environment or Fenway Park. It detects real threats. It's got some built-in capability to identify people who are on a watch list, and it's built for complex environments. I'm going through quickly on this because I think it's important to sort of understand this is machine learning in the wild, so it's not just detached research machine learning. It's how does it come together for a product that solves a problem for a customer. But I do want to kind of get into what are the interesting attendant problems. So that first product, Edge, is being shipped across the world right now. We've got 12 of them, and they're in almost 12 different countries, and en route to our initial ramp, our initial rollout. In Q2, shortly after that, we're launching a surveillance product that's going to be able to connect to existing cameras and analyze video streams. So the goal of that is to take what is a incredibly burdensome tool for operators and make it less so, make it actually work for them. So video cameras are used for forensic purposes almost exclusively. I'll make a claim that I have done no research on, but that it's the lowest value per bit of data that there is, period. I think it's just these cameras that you see like these are going to a storage closet, never to be looked at again unless something happens. And in a lot of places that's okay, because there's really nothing that they're looking at. This is probably like a 24-hour co-working space, what's happening. But for a lot of people that truly need to make sure that their facility is protected, where there is a threat of somebody coming in, then they need something that can alert them in real time, and today, those systems come with huge levels of false alarms. So we're trying to put everything we can on the technology front to bear to reduce the number of false alarms, and our goal is fewer than 10 per camera per month. That's the number that unlocks actual surveillance, which does not exist in real time today. So we use a combination of AI and training. We have a really neat process for continually updating based on input from humans. I'll get into that.
Do you have a similar goal for the negatives as well? Things that you might miss?
Yeah, so we have a goal for the negatives. What's interesting is that there are never complaints from customers about the probability of detection. The probability of detection is sort of, it doesn't correspond to a customer pain point, if that makes sense. So so there is a metric around that, and it's just not, as you think about how do you deliver something that really does a job for a customer that they want to do, that helps them make progress. It's about taking noise off of their plate. It's not about generating more data for them. It's about paring it down by an order of magnitude, by a couple orders of magnitude. So examples of the kind of video that we look at, here's a loading dock sped up with people in forklifts. There's a camera outside of, I think, a car dealership. And we don't control the camera, and we don't control the way the camera was set up. We certainly don't control the scene. So we have to be able to handle all of those. I think the middle one is played as well. We have to be able to handle all of those factors if we want to be able to just deploy this all over to anybody. So I've got a couple more videos, but you can see the kind of imagery that we're talking about here. It's typically pretty low resolution. Cameras can be 10 years old and have not been swapped out. All right, so on to for the surveillance product first. I'll start there. What are the problems that we're solving here? So one is, how do you detect and track objects in video at scale and in real time? And that comes down to the models that you use, the architectures that you use, as well as the platforms and the systems design. Number two is, how do you robustly detect people despite a huge variation? And then number three is, how do you make use of salient motion information? And there are a variety of reasons why you'd want to do that. So we use convolutional neural networks to solve the problem of object detection. And I'm not going to talk too much about convolutional neural networks because of their prevalence, but I will talk about what have emerged in the past year as the leading detection meta-architectures, so what you can think of as meta-architectures. So in real-time video analysis, in real-time object detection in video, there are really three leading state-of-the-art approaches that have converged on a single methodology. And so that is using a single convolutional neural network for feature extraction, and then having a mixed objective of regression and classification. So they're broken up into these parts where you have a feature extractor, something that is doing what is typically called region proposal, and then something that's doing classification. And they use a sliding window style prediction. So I think an easy way to talk about how these came about is to talk about this center one, which is called faster RCNN. The one in the upper left is single shot multi-box detector, and the one on the lower right is region-based fully convolutional neural network. But all of them have this common, those common elements that I just mentioned. So how did faster RCNN come about, and will there be a fastest RCNN? No, I'm just kidding, I don't know. But so RCNN was one of the, it was a paper by Gershik, and it was among the first modern incarnations of convolution-based object detectors. And it did a very reasonable thing, which is it had a step that was external to the convolutional neural network that was computing different regions. So it was an externally computed region that would be then used by the neural network to classify each one. So if you imagine that's our large image, it would generate many, many different regions and then run each one of those little patches through the convolutional neural network. So there's a lot of duplicated computation from that. So it was pretty fast if you defined it as the RCNN piece, but the fact that you had to do this external computation and you had to do it many, many times on every piece of the image made it actually very slow, not capable of doing real-time object detection at scale. So then with fast RCNN, it uses still this external box computation, finding regions of the image to look at, but then it crops the features at an intermediate layer in the convolutional neural network so that you aren't repeating the feature extraction computation, and you're just doing the rest of what comes, which is a classification portion. So again, still has this kind of expensive external region finding step that's having to compute, and then you're going into the convolutional neural network at a crop after you crop the features. What faster RCNN did is they figured out a way to have the image go once through the convolutional neural network and to have both the region generation happening using those convolutional features and the classification using the same convolutional features. So the incremental cost of proposal generation was now tiny. It's single-digit milliseconds. So I hope that made some sense, because this really is powerful. And if you look at, as of November 2016, the submissions to the COCO server, half of them are based on faster RCNN in some form. So what you find is that if you're talking about real-time video based object detection, you're talking about one of these meta architectures more than likely.
Question?
Yeah.
When you talk about a region, are you talking about the region around one person that you're tracking, or is a region typically larger or smaller than that?
It is so region is class agnostic. I mean, I'll repeatedly talk about people because that's a primary concern in security, but really, and I should have, I guess, explained that, is that you're trying to find any regions that may contain objects, and then you're trying to classify those regions as either an object you care about or not. And the old school way of doing it would be to search across the frame and across the scale space. You could go pixel by pixel, or more than likely you jump pixels, and generate a bunch of proposals that may or may not be things that are interesting to you, and then you classify them as either person or bird or car or whatever. Does that make sense? So
Yeah.
those regions that are generated are at different spatial positions, different scales, and different aspect ratios, but they're all class agnostic. It isn't until the classifier portion of it that you get a decision as to whether it's a person or something else.
After you've generated the regions, is it expensive to track motion?
Yeah, it is. And so I kind of break that out separately in the talk, but it's a really important point that if you've gotten this far, if you're using faster RCNN and you're talking about a video, you right now at this point with just that tool, you are treating every frame as an independent look, and so then you have an unsolved problem, which is how do you make those into one unique object, and then there are other reasons why you need to incorporate motion, but I'll talk about that in just a second. All right, so as a practitioner, how do you choose which one of these to use? And it's it's not obvious that those are the things, but we've spent quite a bit of time analyzing it, and so those meta architectures are really powerful, but how do you choose? Because there's a trade-off between, I said I was going to be looking at that, so now I'm looking, but sorry guys. I said there was going to be there's a trade-off between speed and accuracy, and depending on your application, you may have vastly different needs for that. So if you're doing a mobile application versus you need the real-time speed of an autonomous vehicle one versus Google, Snapchat, server-side computation where you can optimize for accuracy, but maybe there are throughput challenges. So you have to kind of look at the different combinations in this space, and they really are like super Lego blocks here. So think back to the last slide on those 3 different pieces. So you get to choose what your meta architecture is, SSD, fast RCNN, or RFCN. You get to choose your feature extractor because they all, not out of the box, but they all can play nice with different feature extractors. So, VGG16 is a really good one, and that's the one that we use. ResNet 101, Inception, they can all be kind of mix and matched with these different things. MobileNet is a fairly recent one, which is a really lightweight one, and so if you wanted that mobile application, maybe a little worse accuracy, but can be supported there, you would use that. So you get to choose your feature extractor, and those are the 2 high-level choices you get to make. Then low resolution versus high, so you can drop it to 300 pixels versus 600 pixels and see how that affects the speed. The number of proposals, so in this region generating step, region proposal step, the default is 300. Looking at an image, default is 300 different boxes, but you can dial that down and sort of analyze, okay, what does it do to the mean average precision if you drop it to 100? And that changes based on the meta architecture and the feature extractor, but you can play with that. And then there are other things, stride, other factors you can change with that. But the point is, you sort of like, as a practitioner, it matters a lot less to us what the training time is. It matters a lot more to us how it performs at test time. And so what is the GPU time there, and what is the mean average precision based on that? And we can sort of find this frontier of optimality along the cyan line that I put there. And that's kind of how we thought about it. Now we're a startup, so we didn't try all these combinations, and some we read about. You can rule out things that are not on that frontier, and then you can sort of also kind of get lucky. So we've found what I think is a good combination, and it's working well. But that's the framework we use to evaluate it. Lastly, on this is you get to choose your framework. So the things that matter there. So the ones that we've thought a lot about are Caffe, TensorFlow, and MXNet. And some of our guys were just out at AWS reInvent, and if you guys are not familiar, I don't know, but Amazon has announced intentions to support MXNet pretty fervently. So what do we think about there? Well, we're a Scala shop primarily. We use a couple different things, and so they have a Scala package that's really good for us. Multi-GPU support, distributed in nature, mobile is good. Being supported by Google in TensorFlow's case is a huge benefit to us. How big is the community? We sort of try to predict, and it's impossible to do. Where is the next thing going to come out so that we can rapidly incorporate it, because we don't labor under the illusion that it'll be our exact configuration in 2017. It's going to be something different. Where is it going to be? And so we don't know. So we've stuck with Caffe for now because it's got a lot of interest from academics, and that's where the the smart people. I shouldn't say that. There are definitely smart people on every one of those. But we've stuck with Caffe for now. In 2017, I predict we'll probably switch, and so it's an interesting thing to think about. Okay, so a little bit about faster RCNN, though I think I really covered it. Trying to think if there's anything that we could really go go forward. The rest on this one kind of goes into even more detail, and I don't think that that's quite as helpful. But this is our system architecture. We have a human labeling step, which I haven't spoken about at all. Well, the reason why we do it is because, one, we want to be able to really quickly incorporate instructive examples from the wild. So we want to be able to see where it's challenged, because you're dealing with all manner of real-world scenes, and we want to be able to rapidly incorporate those. So by having it report out what are the maybes, then we have a nice way of doing that. Another reason is that we want to avoid what has been like the historic, and it's related to what I just said, but the historic brittleness and the historic false alarms that people have had. So right now, you either go all human to monitor your video, which is impossible. And I think the Israelis at Ben Gurion Airport have 100 people monitoring 1,100 cameras. Even that is not the right ratio for people to actually physiologically monitor cameras, and that's absurdly expensive. Or you try to do it with video analytics, which give you a lot of false alarms, or you have a monitoring operation where you have people who are remotely kind of monitoring your site. What we're trying to do is have a 95% solution for the customer that's driven by AI, that's sort of training and bootstrapping itself, but that has the ability to kind of give you validated alerts for those really tough cases that you're just not today and maybe not in 5 years going to be able to handle because of the level of nuance. All right, so shifting over, that was kind of the scale discussion. How do you do it at scale? How do you do it in real time? The next thing is dealing with this humongous variation. This is video from customers and from training sets and things like that. So one is that the video is low resolution in some cases, and going back to sort of faster RCNN versus that other one, SSD. SSD is 10 times faster than faster RCNN, but it's not good at dealing with small objects in low resolution scenes. So other people can use it, we can't. We've got it up and running and we worked with it, but in video surveillance, the resolution is so crappy that a person will look like a fire hydrant in these tiny little low resolution scenes, and so it's a major limitation. So this is a tough thing that we try to deal with. Noise and compression artifacts, especially in low light condition, you've all seen how that kind of video looks. Lens distortion, color gamut, the reproduction of color across cameras is not consistent, and that's really challenging. The appearance of people in Boston in this weather look very different from people in Florida, and if you have a training set that includes no winter coats, that's a problem, and we've sort of discovered that. So people drive golf carts, forklifts. I showed you a couple of those things, so you have to account for that. So there's been a lot of work that we've done on making sure that we have a strong data set that captures these variations. Weather is another huge thing. So we do some augmentation, put a lot of thought in general into our data sets. I think I'll go on from there. So you had a question about motion and tracking, and because it was a little confusing to me initially, I made this really high quality drawing. So what you have when you look at these scenes is, well, I sort of mashed everything, put everything on this one slide because I figured I could talk to it as a framework. But so imagine a person is walking from left to right. In the left-hand part of the screen, you have really good detections on them. And so that's great, but you have the problem of a bunch of overlapping boxes that you want to treat as one person, and you're only looking at it independently, so how do you do that? In the middle there, the person does something weird, and maybe they bend over and they don't present as a person, or maybe they become partially occluded, but they stop looking like the kind of person that you would want to have in your training set. That sounds funny. But yeah, they stop looking. You wouldn't want to include those images in your training set to get them, so you have to get them another way. And then you regain them at some further frame. You want to be able to stitch together the blob that was between those two detections. And then lastly, you can't really see it, but I've made these bolder right here, because speed is such an issue that it's nice to be able to track or do your full-blown classification every n frames, and then use tracking between those frames to fill in the information. Even if you could have gotten a reliable detection on the person there, you might want to do that to speed things up. So we noticed that this was the way that tracking was going to factor into our problem. We noticed that motion was so helpful in some of those scenes that you saw, like people crossing the prison fence scene, and they were just looking like roly-polies kind of thing. So then we put a lot of time into understanding what we were going to use to try to solve for each one of these, and there are really two methods that you need. One is tracking by repeated detection, also called tracking by detection or tracking by repeated recognition, and that's kind of deep learning tracking, because all the deep learning methods are going to be generating classification, and you've got to stitch them together. So a really good, we've got to take all that and just constantly be reconstructing and classifying in real time, so that in less than a second, that person steps through and you can see that you get an indication whether they have something on them or not. So I started by saying, why do we use phenomenology instead of image? One is because we're like a cheap webcam when it comes to the millimeter wave hardware, and that's so we can make the system very inexpensive, very sparsely populated. The other is that we have a team of physics types. So I can't remember if Jan LeCun wrote it or objected to it, but there was something about small data, and he said, the types that deal with small data are ones that have walked in the shoes of physicists or electrical engineers previously in past lives. And I think part of our team, we have, on the video side, we have a deep learning focused team and have done doctorate work in that area. But on this side, it's computational electromagnetics, it's metamaterials, it's electrical engineering. So I think people gravitate towards that. They understand the phenomenology, so they hand engineer features based on material properties and geometry that make this thing work. And the good thing is it does work. So they've built this, it's all ready, and it's being used today, albeit in pilot form. So I talked about it a little bit, but we have those three key core sensors. Millimeter wave is a line of sight technology. It kind of bounces off of you. HF is not. It can see any magnetic field disturbance. Electro-optical obviously is just looking at line of sight, and it's all flying at the machine. We're processing it all really quickly, reconstructing it, doing this classification based on material and geometry, and then we're doing just traditional kind of region growing to find to find segments, small parts of the body that have a threat or do not have a threat. So a challenge here, as I've said, is minimal latency. It's got to happen really fast, and it's really interesting data that we're able to kind of exploit. This is, I think, a little bit too detailed, and more importantly, it's hard to read. But it's the same. It's showing the same thing. This is kind of the workflow that we use for doing a bunch of these intermediate steps. So now what we're looking at our company is, okay, we got it to work with features that we've designed. How can we use some of the advances in deep learning to be able to strengthen what we've got working? And so we're excited about that in 2017, and I suspect many of you are now or were at startups. You understand that you sort of have the imperative to make it work. We've done that, and now we're trying to see how we can extend it with techniques that are more exploratory. Because using deep learning for video is not exploratory. It's just like you have to do that if you're in the realm of video analysis. Using it for millimeter wave and for magnetic field sensors, it makes a lot of sense, but it's not a slam dunk, and it's not easily ported. At least we don't know that it will be. So lastly, what tools are we using? I hope this piece is relevant, but we've tried to think about how we set up a system that makes use of the super Lego blocks and that can easily swap in things as they come online, because more so than ever, what we're using today is not going to be the state-of-the-art thing in 6 months, and so we've got to be able to rapidly incorporate it and have the training infrastructure, the data, all those things that are harder to swap in be really robust. So we use reactive programming and reactive systems approach. We use microservices. Each thing in our system does one thing and does it well. It's small, self-contained microservice, most of which today run in the cloud, but many of which can be put on device to do core things related to video processing and so forth. So, we're always dealing with facilities, like actual facilities, and so there's always some on-premise, well, I shouldn't say always, it doesn't have, we could get video from the cloud, but typically there's an on-premise piece, and so we have to have flexibility to deploy what was made for the cloud onto the local environment. And I have this lightweight virtual machine containers, durable communication, messaging-based approach we use RabbitMQ between these services, and reactive languages, framework, and design through and through. A lot of this is by virtue of having us kind of wanting to do it that way, but really the person who's responsible for bringing it is Brian, who worked on the Game of Thrones and Star Trek games, because to make a game as complex as one like that supports tens of millions of active users and can plug in a bunch of different pieces of it, you have to use a resilient approach like that, and we're excited about what it could do in the realm of security. So, ways to kind of keep in touch. We write a blog. I can't say that it's going to be generally interesting. I write some posts. They're okay. I'm working on making them more interesting. But we have a great team in Waltham. We're hosting a Scala meetup that, if anybody's interested in Scala, can come, but it's wholly unrelated to this. But that's our first effort to try to kind of get out into the community. Because when you're working in an area like security and you're out there in Waltham, it's a little harder to kind of interact with you guys down. Well, maybe you guys are based in the suburbs too, I don't know. But it's harder to kind of get down here. So that's what I've got. Thank you again. It is really an honor to be able to share what we've done so far. And like I said, I look forward to sitting in on future talks.
So we do have a little bit of time for Q&A. If anyone has any questions, now would be the time. Yeah.
Yeah, so, millimeter wave, and in fact, looking at the physical shape of the human and giving you signals back.
Yeah. Yeah.
And if someone's carrying, so my real question about that is, if someone's carrying explosives, can you necessarily distinguish that from just the normal, the shape of that particular individual? That seems to be a hard task.
It's a hard problem through and through, but you sort of imagine the transmitter. So on our system, any transmitter anywhere can be picked up by any receiver anywhere. It's bouncing all over. Transmitter goes out. I'll do it on me. Bounces off a person, and if there's an anomaly that's between the person and the transmitter receiver pair, then that active millimeter wave pulse will be distorted in some way, and the skin is very reflective at the frequency range that we're talking about, kind of the 24 to 30 gigahertz range. That's one of the reasons millimeter wave is so good for this. So the skin is very reflective, bounces it off, but it's gone through this anomaly, and the way in which it distorts the signal can be kind of clustered in. I can't show because the threats that we use are made in conjunction with FBI and TSA, and we work closely with them on what the actual threats are, the simulants that we use in our lab. So I have this really nice chart that I can't show, but it has different clusters of the region that show how they are going to affect the pulse. Because they'll do things like they'll change the amplitude, they'll broaden the pulse in characteristic ways that are largely irrespective from geometry. And then the other piece of it is, so that's material, the other piece of it is geometry. So if you had a block of C4 and a wallet, they had the same geometry, they would show up differently on the material front. But then, you know, common objects have a certain geometry to them, like keys are very they'll have a certain way of scattering the millimeter wave signal. So then we can also pretty nicely model the geometry. But, you know, and the last piece of that is we are able to kind of get a body model based on what the reflection is off of just the normal body. So yeah, it's a really, all these things come together.
And out of 100 people walking through that device, will you catch all 100 if they happen to be a threat?
Yeah, well, so, yes, I don't want to answer yes to that. But we look for threats that cause mass casualty, and so you can have tiny bits of explosive that are artfully concealed, and that's what an aviation checkpoint is designed to weed out. For us, it's what is going to be capable, what implement is going to be capable of causing mass harm to a crowd. And we cast these sort of overlapping nets, like porous nets, when we look at millimeter wave, magnetic field, and the electro-optical, with the hope that one of those things is going to find them. In practice, we found that our detection is very, very high for the threats that are considered by our customers to be mass casualty. If you want to detect tiny little things, it starts to get very hard to separate between small clutter in the pocket and small, tiny bits of explosive. So we tell customers that they have the option of doing that, of going into that mode, but it's up to them. Most of them don't want to do that.
Do you deal with people, I'm sorry, this is the last question. Do you deal with people who are carrying backpacks?
Yeah, we will to some degree. So if you're carrying a backpack, you'll hit as an anomaly if you're carrying it on your back. It'll look a lot like maybe like a vest, a suicide vest, but if you take the backpack and put it down by your side and walk through, then you can get through with it just fine, and we can detect metallic anomalies in it. So 2017, a couple of the research areas or really product development areas that we're looking at are how do you do a kind of companion baggage thing. It's a tough problem, all of it is. Yeah.
The material analysis that the millimeter wave does that penetrate the backpack material, or is that where you have to rely on the other methods?
No, it could, based on the material of the backpack, but it might not. And so we're relying on HF. We're relying on the magnetic field for that. Millimeter wave is not suited to baggage screen. It can go through certain materials, drywall. We built, just as like an experiment, something that can like image the inside of your wall really, really nicely. It looks awesome, and you can see things that are like the size of a fishing wire. Why am I saying that? Oh, and yeah, but it's not good. It's not the right modality to use for just doing a screening of a backpack. So we're working on other stuff for that.
Are there examples of collaboration where entities or organizations that are ordinarily siloed can start to cross-reference data in your cloud?
Not today, based on where we are in product development, but we definitely want to do that. So, you know, we have customers that are airports, not TSA, because TSA cares about the checkpoint. Airports are more concerned about their perimeter, and so there's probably, you know, collaboration we can create among them, similar to mass transit customers. That's exactly what we want to do, but we don't today.
Or even like context data of like, over these cameras not owned by the airport saw dangerous materials being loaded into this van.
Yeah.
Another customer saw the van move to the airport, and then the airport sees
Yeah.
before it even goes there.
Yeah. The early adopters are not the municipalities that can kind of be the glue that tie it together. So right now that's not the case, but it's very true. I mean, I know in Boston area there's that kind of collaboration does happen. So that can be, tech enabled by our platform, but we don't do it today. Yeah, I should go to this side, sorry.
Have you done a bit more about how you guys approach training data? I'm imagining like there must be a problem where you don't have that many positive examples of things actually going wrong. And you mentioned data augmentation. I'd love to just hear more about where you get data to train on.
Yes, so there are a few older training data sets from the government that you can obtain access to, and they're older, and that's nice because they represent kind of poor imagery, as opposed to even the autonomous vehicle data sets today are they're not great imagery, but they're better than what you see in a surveillance camera. They're made for traditional computer vision, traditional tests, which means that not every frame is labeled, which is very annoying because you can't just then splice them and go right into your system because you're feeding your system with a bunch of negative class labels on people that are there. I don't know if they don't consistently label because that wasn't the way that those classifiers worked at the time they were created. But what we sort of do is to take a bunch of data sets that were for autonomous vehicle purposes that have pedestrians and things like that. We skew the data set towards overhead imagery because that's a special challenge, and most surveillance cameras are at an overhead vantage point. And then we mix in data that we get from our customers. So we've been lucky to have customers that are willing to have us use their data to be a part of a training data set. And I think, I hope that continues to be the case. There's high concern that they know who's looking at the data and so forth, but there's not a lot of concern about it being factored into the AI. So that's nice. We've thought about other things to do with like more sophisticated augmentation. And so a couple of examples that I've seen that are interesting are recolorization efforts, like to recolorize Civil War photographs. And why that's interesting, and we've done nothing with it, we just looked at this, is that you notice in some of our images that it's like a person with a dark coat in a dark environment, maybe a dark brick background. And so having some semantic segmentation knowledge is nice, and what the recolorization techniques do is to, in an unsupervised way, take a color image, make it grayscale, and make it then reproduce the colors. And in so doing, it develops a nice understanding of the segmentation of the boundaries between objects. So that we think would help us. We haven't done that yet. Other things are virtual environments are really seem promising for some papers that came out of NIPS showed this, and so could we synthesize a lot of data that looks more like somebody in a surveillance scene when you don't have that many examples of people crossing perimeters when they shouldn't. So we have one here. We have a really nice data set that was hand collected by a government to deal with the intrusion thing, but eventually we'll be looking for more. And then the best training data is again our human in the loop training data.
With the human in the loop, do you imagine that you'll allow your models to be customized to either a specific location or perspective, or